Let me start. Good morning. I'm Chijung from University of Virginia. I'm going to present our paper, SwarmFlawFinder, Discovering and Exploiting Logic Flaws of a Swarm Algorithm. In near future, we may be able to see the drone swarms more commonly like this figure. Swarm robotics utilize individual drones and they have been developed to conduct challenging tasks in collective way. Also, drone is already complex and the swarm is more complex. With the complexity, a lot of logic flaws can be overlooked and or become hard to find. So we have worked to systematically find the logic flaws which essentially act as a software bugs in swarm algorithm that adversaries can exploit. In this example, we have a swarm of 4 drones carrying an object using strings, and it's trying to deliver to the destination. And during this, it comes across a moving obstacle which it tries to avoid. And in the real-world experiment, we represent it with another drone. Then an adversary controls an external attack drone to fail this delivery mission. So what an adversary does is, it initially flies the attack drone toward the incoming victim swarm. When it gets close to the swarm, it essentially puts the leader drone at an angle that it crashes into the obstacle. And so the adversary fails the mission entirely. Typically, this swarm algorithm can avoid obstacles well. However, it fails under this scenario. We want to see what's going on. So logic flaw is a software bug existing in the decision-making logic of the drone or swarm. The root cause of the previous example is that this swarm algorithm's multi-force handling is naive. For the leader drone, there are 3 forces applied here. First force is the one used to go forward to the goal. And the second is the force used to avoid the obstacle. And the third is the force used to avoid the attack drone. This algorithm computes the final direction by simply taking the sum of forces. The issue here is that algorithm doesn't prioritize well. Drone should focus on avoiding crash rather than going toward the goal. So this simple resulting vector leads to a crash. Such a type of logic flaws are supposed to be discovered early on. So we want to test the swarm algorithm more to discover logic flaws. However, testing swarm algorithm is not easy. First, swarm is highly dynamic. So to test swarms effectively, it's desirable to run testing under diverse scenarios to cover various swarm behaviors. However, swarm's input space is too large to cover in practice. Coverage-guided fudging serves similar challenges. However, swarm robotics execution is iterative. Code coverage metrics traditionally used in the fudging techniques are not effective. Even with a few tests, majority of the code and the branches are quickly covered without covering diverse behavior. So we need the metrics that can measure swarm behavior. So we introduced SwarmFlawFinder. SwarmFlawFinder is a gray box fudge testing technique for swarm robotics. We introduced attack drones to obtain more diverse swarm behaviors by disrupting the swarm operation. And we use a novel metric for measuring a given test effectiveness. Let's see how SwarmFlawFinder works. This is an overview of SwarmFlawFinder. Let's walk through this one by one. So first, SwarmFlawFinder takes a target swarm algorithm and the swarm mission as input. And on them, it runs an initial test with attack drones. Next, if a test mission finishes successfully, it conducts a test evaluation. Now, this part is the core technique of the SwarmFlawFinder. Here, execution perturbation is done using the counterfactual execution. This will be explained in greater detail in the upcoming slides. And based on the result of the test evaluation, SwarmFlawFinder mutates the current test and the continuous testing. If a test leads to a mission failure, the current test configuration is obtained as output. And it repeats this process until it reaches a predefined timeout. Let's take a look at each step one by one. On the right side, on the right top side is a minimap of the overview. And the yellow highlighted part is the test run creation which is the first step of SwarmFlawFinder. Let's look at this step, test creation. We define test run as two vectors. Attack drone's pose is a point in a 3D space where it is spawned. And we have 4 strategies that attack drone is going to use. One is it pushes back victim drone by flying against it. The second is it chases a victim drone to interfere. The other one is attack drone flies between 2 victim drones to separate them out. While the last one is it flies around the victim swarm to manipulate it. These are basic strategies we want to show. Even with these basic strategies, our technique is effective. These attack drones pose as strategies are the target of mutation. So in the next step, for each test created, we execute and evaluate it. To evaluate the effectiveness of each test, we see if current attack drones pose as a strategy resulting in a new swarm behavior, we consider it effective as we have more hope to find new logic flows from the new swarm behavior. Then we change attack drone's pose slightly with the same strategy for the next test run, because we want to search around the current test run. For example, when test 1 is current run and it shows us new swarm behavior, test 2 is set closely with the same strategy. But if the current run shows similar behavior, we take a big mutation to induce new behaviors. For example, when test 2 shows similar swarm behavior, test 3 is away from test 2 with a different strategy. However, our question here is how to know which swarm behavior is new and which swarm behavior is similar. To solve this, we need the metric that can abstract the swarm behavior. And for this, we introduce a degree of the causal contribution, which we call DCC, that is based on the counterfactual causality. Let's see what is DCC and how it works. We focus on the impact of external factors such as obstacles or attack drones on the victim drone, where the impact can be intuitively measured by drone's reaction to them. We do this by counterfactual causality, which basically captures that the impact on B if A had not occurred. And this causality dependence in swarms we capture through alternative executions of with and without external factors. So let's take a look at this example. On the left side, we see the original execution, and on the right side, we see the same alternative execution just without the obstacle. Now the obstacle over here acts as A in our counterfactual causality. So compared to the original execution, as you can see here, removing the obstacle changed the flight path of this drone. So we captured the impact through this delta, which basically is B. Now to compute the DCC, we run the alternative executions for every external factor. In case of follow 1, we first run the original execution, then we remove the obstacle and run the same execution. From here, we get the delta and store it. Then we do the same for the leader and the follower too. And as you can see here, we get the different deltas in each of their essences. And by storing both of deltas as aggregated percentages, we end up with the DCC values for the follow 1. For each time interval, we get separated DCC values as shown below. So we accumulate these numbers throughout the entire swarm mission. So you can find that the worst impact to follow 1 is reflected by the light green region. And also, third worst impact is also shown like this. This DCC stream is for follow 1. So we collect this for every drone. We use this DCC as the metric for swarm behavior comparison. Now, to see how DCC compares with different executions, we use the NCC value. NCC is basically the normalized cross correlation, which is one of the ways to compute the similarities between the data in various fields. So for this example, you can see the DCC of two exclusions, and as you can see, they are quite different. This difference is reflected by NCC of 0.65. We use the threshold of 0.87 to categorize whether two exclusions are similar or different. While on this example, we again compare DCC with different exclusions. So you can see that two graphs are quite similar. This is reflected by NCC of 0.92. Since it's above the threshold, we categorize them as similar. So now, to see how it works, we start by finding logic flaws in real-world swarm algorithm. And we evaluate the effectiveness of DCC in fudge testing. And for this, we compare our approach to random testing not having any DCC guidance. So let's start with looking at each of the four swarm algorithms. For the first algorithm, adaptive swarm, its objective is multi-agent navigating. It has 4 drones, and we find 20 unique logic flows. We find 6 root causes and potential fixes, and all of which are confirmed by the developer. And for the second algorithm, Socratic swarm, it aims to do a coordinated search. It had 8 drones. We find 8 unique logic flows, and identify 4 root codes and fixes. Again, all of these are also confirmed by the developer. And Shadro and Pietro's algorithm conduct distributed target search mission with 10 and 15 drones respectively. More details about both algorithms are in the paper. And for evaluation of the effectiveness of DCC, we create a random testing approach by removing DCC-based guidance from our approach. So unlike SwarmFlawFinder, in this random testing, the only feedback is the execution result. So if a test run results in mission failure, it's considered as desirable, then it takes a small delta. But if a mission has no failure, it mutates the current test case more. We run the random testing approach and the SwarmFlawFinder on our evaluated algorithms for 24 hours to measure the spatial distribution of the test cases. This is from random testing, and each dot spatial meaning its attack run's initial pose in each test run. The larger dots mean the test cases show unique swarm behavior, while the smaller dots lead to non-unique behaviors. And each color means whether the mission is successful or failed. And this is a spatial distribution from SwarmFlawFinder, and this is the victim swarm location. You can see random testing distribution is way more spread out, and this shaded area is what SwarmFlawFinder tests. From this, we observed that our approach can focus on smaller but more promising data. And for unique swarm behaviors, you can see there are more dots on the SwarmFlawFinder's test cases. It finds 2 times more unique swarm behaviors than the random testing. And for mission failure cases, we observed that SwarmFlawFinder finds 25% more overall failures than random testing. Also, for the unique DCC value outside of this gray shade, it seems that random testing finds some unique test values from the places that our approach did not test. But we manually check them and find that they are all variants of the tests generated by SwarmFlawFinder. So far, SwarmFlawFinder finds a total of 42 unique mission failures from 4 real-world algorithms. And we identify 15 different root causes and potential fixes, and they are all confirmed by the author. Also, it finds 2 times more unique DCC and 25% more failures than random testing. This is a case study about finding logic flows using SwarmFlawFinder. This mission is from the first algorithm we use in the evaluation, and this photo shows this example reproduced in the lab with a real-world drones. So in this mission, 4 drones are moving toward the east along the wall. And the attack drone's strategy is pushing back leader drone. And you can see attack drone is approaching toward the leader drone, and it pushes back. Because of which, one of the followers crashes into the wall. This is because when attack drone pushes the leader drone moves into a follower 3, and in doing so, the follower 3 crashes into the wall while avoiding the leader. The root cause here is that the leader drone does not consider follower 3 as an external object. We manually check source code and find that there is no code to implement that logic. So to solve this problem, we copy and paste the follower's logic that detects other victim drones, and the developer confirmed the root cause and fix. And more case studies can be found in the paper. To sum up, we propose a novel fuzz testing approach for swarm robotics using a new feedback metric. We conduct evaluation, and its results shows our approach is effective. Also, all logic flaws and the potential fixes are confirmed by authors. This is my end of presentation. Thank you.
All right, questions for the drones.
Hey, this was a great talk. I was wondering, in coverage-guided fuzzing, there's usually a saturation after some amount of time. Did you find similar saturations here?
Yeah, yeah. Thank you. Actually, the main goal of this fuzz testing is finding unique swarm behaviors, which is unique DCC values. And as you mentioned right before, we observed that after around 9 hours, the number of the founded unique DCC values are saturated. But in this evaluation, we conduct all experiments for 24 hours for each swarm algorithms. So yeah, saturate after around 10 hours.
Great, thank you.
Yeah, thank you.
Hi, very interesting work. I have a question. So it seems like your metric DCC is kind of like measures the deviation of the drone from its original position. I see like in your case study, like you have obstacles. How do you like measure those, like the distance to those obstacles, like to trigger those bugs?
Okay, thanks for the question. So your question is essentially how do we measure distances from the obstacle from all these swarms? So the way we do is not actually measuring the distance from the obstacles to the swarms. So as you see, we run those counterfactual executions, and then we see the deltas. So we remove all these obstacles. So essentially, when we run the alternative execution, we remove the wall, the existence of the wall. And then the swarm will behave differently. How much it behaves different is essentially the impact of the wall to the swarm. So that is kind of similar to what you think, how we measure the distance from the wall to the swarm. So yeah, we don't measure the distance, but we measure the impact of the external object to the swarm's behavior.
So like during the testing, so you don't assume any obstacle. It's just like you measure its deviation from the original position, and then it may like trigger some bugs, like if I have the obstacle.
So you remember that we have those counterfactual execution, that the definition that if if A would not happen, if B did not occur, that kind of things. And so when we run those alternative executions, we remove each of those external factors. So if there is 10 different, for example, external factors, then we run 10 different executions. So each execution will give us the idea of the impact of each the external factor. And then we aggregate all of those. So I think it's a little bit complicated to understand, but the way we do is we we run multiple executions and remove one of the vectors at a time, and then try to understand that the impact, and then we aggregate all of those to understand the aggregated impact of all the external vectors to the swarm.
Thank you.
Okay, nice talk. So I understand your testing assumes there's only one attack drone. If you have two attack drones, would you find additional flaws? And where does as you increase the number of attack drones, where does everything stop?
Thank you so much. So the question is essentially, we only tested with one attack drones, and what happened if we have more? And the answer is, of course, if we have more drones, then we can squeeze more. But our goal is essentially try to find the most cost-effective and efficient attacks. So for example, like if we have a bunch of swarms, like for example even 10 drones of the swarm, if we can rack their missions with only one attack drone, that would be really nice. With more, actually we test more and then we find more the attacks, and it's much easier. But we want to show that even only one, we can find a lot of flaws. And yeah, so yeah.
Yeah, so the threat model is a complicated thing, is how much the attack drones cost versus how much your drones
That's
cost,
right.
etc. If you wanted to do this thing with 3 attack drones, would be infeasible, or would it just take a little bit more compute time?
Yeah, but much easier. If we have more attack drones, and then we can actually rack it much easier, much faster, and then much catastrophic. Some of those logic flows that we find is kind of interesting, that we are not actually racking the drones. We don't actually, our goal is not physically harm the individual swarms, but just exploit the fact that the algorithm has some of the flaws. So for example, if we push some of those swarms into the particular direction, and then they have some of the flaws, they have to stuck in some places. They couldn't make a progress without any physical harm to the victim swarm. So we are kind of looking for that kind of things. And a lot of reviewers and also a lot of other researchers, when we talk with this research, their first question is indeed something like, you can just attack the physically, but our answer is that's probably too straightforward, and then we want to look for more sophisticated and stealthy attacks, and then cost-effective.
Yeah, actually, I was asking about the computational power that your analysis takes. So if you add more attack drones, do you run out of does the amount of computation power that you require grow exponentially or just linearly?
I see. So that part, so your question, the next question was, if we add more attack drones, how much more computation that we need to do to conduct this experiment, because we run a lot of experiment depending on all these external factors, including all these attack drones. So the answer is it's not exponential, but it's kind of linearly growing, and then we have that one in the paper. It has a little bit of the equation, so it would be great. I believe that one is in the appendix, right? Yeah, we have that one in the appendix. We have some equations, how much attack drones, and then how much computation you're gonna have, and then that's the thing. Yep. Thank you.
All right. Like a 20-second, 30-second question.
Okay. Yeah, this is great work. This is Hyung-seo from Purdue University. In my understanding, if the swarm algorithm is screwed up, the crash will be happen. But in real world, as far as I know, each drone control software also equipped with their own collision avoidance algorithm. So have you guys considered such cases?
Yes. This algorithm actually has 2 parts. One is the global planning and also swarm algorithm, and also the local planning. So it does indeed have their own logics to avoid all these things. But what we find here, exactly this bug is, so they are kind of competitions between the swarm wants to maintain whatever their goal has, and then there is also the local planning they want to avoid. And in this case, those the swarm algorithm override their local planners' the logic. So we are looking for that kind of subtle differences, and that's also why we need to test a lot. Thank you.
Thank you.
Chijung, That was a phenomenal talk. Thank you so much. Let's all give it up for Chijung. That was great. Woo! All right.